Somewhere in a landfill right now, there is an $800 washing machine that died before its 7th birthday. Not because it was abused, not because the motor exploded. It died because of a rubber seal the size of a bracelet and a design decision that turned a $4 repair into a full machine replacement. This video is brought to you by the Durability Project, where we explore why the things we buy no longer last and the engineering decisions that quietly shape their lifespan. And the strange part is, that decision wasn't random, it was engineered. Once you see it, you'll start noticing it in almost every modern appliance. The seal is pressed against a bearing hidden deep inside the drum assembly. When that seal fails, water reaches the bearing, the grease washes out, rust begins, and the drum starts to grind. And here is the part most people never see. That bearing sits inside a plastic outer tub that was welded shut at the factory. No bolts, no seam, no practical way to open it without destroying the shell. In many cases, the official repair is replacing the entire rear tub assembly, a repair that can cost hundreds of dollars in parts alone. The irony is that the bearing itself is usually a cheap commodity component. But the real change was not the price of the part, it was access to it. This video is about how that happened, not by accident, by design. One engineering decision quietly transformed a small repairable component into the failure point for an entire appliance. And once you see that decision, you cannot unsee it. To understand it, you have to look at a very different kind of washing machine. Somewhere in rural Ohio, in a barn that probably hasn't seen a fresh coat of paint since the Eisenhower administration, there is a 1960s Maytag wringer washer that still runs. Its bones are cast iron, its tub is porcelain-coated steel, and every bearing inside it is reachable with a standard socket wrench and a free Saturday afternoon. That machine was built with an assumption modern appliances often ignore. Someday, someone would need to get inside it. Repair was not an accident. It was part of the engineering. The outer tub was two separate halves, bolted together at the equator with a rubber gasket seated between them. Those bolts mattered. That gasket mattered, because that single design choice meant the bearing at the center of the machine was never permanently sealed away from the outside world. If it wore out, you did not throw the machine away. You opened it. The bearing could be reached. It could be replaced. It could be saved. That accessibility was not a happy accident. It was a philosophy baked into the engineering from the start. The people who designed those machines assumed that sooner or later, someone would have to open them up. Repair was treated the way a bridge engineer treats an inspection walkway. Not optional, not decorative, but necessary. The machine had to survive its first decade and its second because a household budget in that era did not quietly absorb a new appliance every few years. It absorbed a repair call. The bearing itself was a simple radial ball bearing pressed onto a stainless or chrome steel shaft. Nothing exotic, a commodity component. Bearing suppliers in almost any mid-sized American city stocked them in crates. When one failed, a technician could separate the tub halves, press the worn bearing out with a shop tool that cost less than a tank of gas, press a new one in, bolt the machine back together, and send it home running again. Parts cost under $10. Labor under 2 hours. A repair, not a replacement. And that repairability created something else, a feedback loop that kept manufacturers honest. Because the tub could be opened, technicians could see exactly what had failed and why. Worn seals, misaligned shafts, bearings that degraded too quickly. Those problems didn't stay hidden inside sealed machines. They showed up on workbenches across the country where mechanics could point to the failure with their hands. Evidence like that has a way of traveling back to manufacturers. Machines built this way lasted. 10 years was normal. 20 years was not unusual. In fact, industry groups later acknowledged that the average lifespan of washing machines fell from over 10 years to under 7 as prices dropped and construction methods changed. That decline was not random wear and tear. It followed a specific shift in how machines were engineered. Because for that change to happen, something had to reverse. Somewhere inside a product engineering meeting, someone looked at a two-piece bolted tub and decided those bolts were a problem. Not because the bolts failed. The bolts almost never failed. The problem was the bolts. They made the machine easy to open, which meant it could be repaired. A machine that could be repaired was a machine that did not have to be replaced. The cast iron and porcelain era was not nostalgia, it was mechanical honesty. Machines from that era were honest. They showed you what they were made of and how they went together. More importantly, they showed how they could come apart again. Bolts held assemblies together. Gaskets separated components that might one day need attention. Bearings had part numbers that existed in the real world, on shelves in supply houses, waiting for the day someone needed them. Then the materials changed. The arrival of injection-molded polypropylene as the primary tub material did more than just change what the tub was made of. It quietly changed what the tub was allowed to be. Picture the outer tub of a modern front-load washing machine. It is a single molded polypropylene shell, roughly the diameter of a truck tire. Inside it, a stainless steel drum hangs on a central shaft. At the back of that shaft, pressed into a housing fused directly into the plastic wall, sits a sealed bearing unit about the size of a hockey puck. That bearing itself is a standard industrial component, the kind of part you might find in dozens of other machines. Polypropylene on its own is not a bad material. It resists water. It tolerates detergent chemistry. It is light enough that a single worker can carry a full tub assembly across a factory floor. It is also inexpensive enough that the savings on that one structural component can help fund the touchscreen control panel, the LED display, and the sleek design that sells the machine in a showroom. The material is not the real story. The real story is what manufacturers chose to do with it. When the outer tub is molded as a single piece or fused from two halves using ultrasonic or spin welding, the bearing housing becomes a permanent part of the tub wall. There is no gasket separating the halves. There are no bolts waiting for a technician's wrench. The joint between the tub sections is not a seam you can open. It is a molecular bond between thermoplastic surfaces. In practical terms, the only way to reach the bearing is to cut the tub apart. And that brings us back to the small component that started this story. The bearing unit inside that housing carries its own internal lubrication. Manufacturers describe it as sealed for life. In practice, that phrase means sealed for the life the manufacturer expects the machine to have. Over time, heat, vibration, detergent residue, and moisture slowly degrade the lubricant inside the bearing. When that lubricant breaks down, the bearing begins to wear. As the bearing wears, the drum shaft develops microscopic lateral movement. That movement damages the seal around the shaft. Once that seal fails, water reaches the bearing. From there, the failure accelerates. Rust forms. Friction increases. The drum begins to wobble and grind. And eventually the bearing seizes or breaks apart entirely. At that moment, the repair math turns into a trap. The bearing itself is a cheap commodity part, the kind of component sitting in warehouses across the country. But reaching it is another story entirely. In many modern machines, accessing that bearing means destroying the outer tub or replacing an entire rear tub section. That plastic assembly is a proprietary part that can cost anywhere from $150 to $400, depending on the brand. And there is another complication. Manufacturers often stop producing those parts only a few years after the machine leaves the showroom floor. So the replacement part either doesn't exist anymore, or it costs close to half the price of a new machine. Either way, the calculation becomes obvious. The machine goes to the landfill. This does not require a conspiracy. No single engineer sat down and deliberately designed a washer to fail. What happened is more structural than that. One engineer chose a welded tub because it lowered manufacturing cost. Another engineer specified a sealed bearing because it simplified assembly on the production line. Each of those decisions made sense on its own, but neither decision was evaluated against the repair bill someone might face 8 years later. Every individual optimization improved the factory process. Taken together, those optimizations quietly produced a machine with a built-in lifespan. Not every manufacturer followed that path. Speed Queen, a Wisconsin-based company known for commercial laundry equipment, made a different decision. Their residential machines still use a two-piece outer tub with serviceable bearings. The design costs more to manufacture, and the machines themselves sell for roughly twice the price of many mass-market models. But the company claims those machines are tested to roughly 25 years of typical home use. The difference in price is not just marketing. Much of it is the cost of building a machine that can still be opened and repaired. At some point in appliance design history, the outer tub stopped being an assembly and became a permanent structure. And once that change happened, the smallest parts inside it took on a new importance. A simple rubber lip seal, a component that might cost less than $1 to manufacture, became the silent failure point. When that seal finally gives way, years after the machine left the factory, the result is already written into the design. That machine in the landfill didn't suddenly collapse. It followed its blueprint. Every weld held exactly the way it was designed to. Every bearing had the lubrication it needed. The machine did what the engineers intended it to do, including reaching a point where repair stops being practical long before the customer expects it. So here's the checklist that actually matters when you're looking at one. Does the tub separate with bolts, or is it fused together as one piece? Is the bearing housing something a technician can press out and replace, or is it molded permanently into the shell? Does the manufacturer still supply rear tub assemblies for machines that are more than 5 years old? Ask about the bolts, not the steam cycle, because once you start looking for the design decisions hidden inside everyday products, you begin to see them everywhere. And washing machines are just the beginning. The next one might surprise you. This is the Durability Project.